Sweet. All right, so we're going to start lecture set 12 today. Lecture set 12 is our last lecture set in the class, so that's kind of cool. We are right in line with where we're supposed to be based off the course outline, which is also pretty reassuring at this point. So we'll finish up, we'll start lecture set 12. We'll get as far as we can in it today. It's not too long of a lecture set, so you can see there's about 30 some odd slides. The last few slides are exercises or cumulative exercise, so not all of it is teaching material. So I'm very confident we'll finish it on Thursday. So we actually will be a little bit ahead of schedule. And lecture set 12 and lecture set 11 will be on assignment 6. So assignment 6 is lecture set 11 and lecture set 12. And that's due December 7th, I believe, or December 6th, I think, next Tuesday, December 7th. December 7th. Okay, and then of course, assignment 5 is due this evening at the end of the day. So should have a little bit of time at the end of lecture to take any assignment 5 questions if there are any. I'll just kind of base it off of where I am in the topics. And I have office hours today from 1 to 3:30. So I wasn't able to hold them yesterday. So I'll have an extended office hour today until 3:30, in which you can come and ask questions about assignment 5 if you have any. All right, so lecture set number 12 is devoted to the study of the regression line. So what we're going to be learning how to do in this lecture set is fit a regression line to a data set, evaluate that line in terms of diagnostic measures. So we're going to look at 2 diagnostic measures, which are actually very similar to one another. They're actually functions of one another. And then we're going to talk about conducting inference based off the regression line. So we'll be taking the same confidence interval and hypothesis testing strategies that we have learned about in the last 3 or 4 weeks. And we're going to apply them in this context. So there's going to be a little bit of new material in terms of, setting up for the inferential aspect. And then we're going to see, again, some hypothesis testing confidence intervals or in the context in which we are examining, within the context of linear regression, is what I should say. All right, so we'll start off with the type of data set that we might observe if we were interested in conducting linear regression analysis. So this data set is actually quite similar to the paired data set that we saw when we studied the pair t-test in lecture set number 10. No, lecture set number 9, sorry, in lecture set number 9. Now, so you'll recall that a paired data set is a data set where each observation emits 2 variables. Right, so here we actually have students, and I think that they were first-year biology students. So this would be student 1, student 2, student 3, student 4, student 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so there's 15 students in this particular data set. Each student is emitting 2 values: the number of hours they slept the night before a midterm, and then their corresponding mark on the midterm. So we have 2 different variables. Okay. But we still have paired data. So the key here is we have paired data the same way that we did when we studied the paired 2-sample t-test, but the variables are different. With the paired t-test, you have the same variable being measured on the same observation. With regression analysis, we're typically going to observe paired data, but two different variables, which is what we have here. So we have midterm mark and the number of hours of sleep. Now, the goal of this analysis is effectively to determine if we can use a model to predict one of the variables' values from the other. So the goal of our regression analysis, or the goal of regression analysis is typically to make predictions about the value on a certain variable given the value of another variable. So we're trying to link these two variables together in order to determine if we can make a statement about one using the other. So this is quite different from what we've seen throughout the class so far, because so far our inferential techniques have been based around making statements about the population mean, or the difference between the population means, or one of the chi-square hypotheses. So here, again, what we're trying to do is link the variables in this paired data set together so that we can make a statement about one using the other. Okay, and the way that we're going to go about doing that is via what's called regression analysis. All right, so again, we want to describe the relationship between two different variables that appear in a paired data set. To do this, we can build what is called a regression line. In order to have an effective or useful regression line, we require that the variables form what is called a linear relationship. And we would have seen examples of this back in lecture set number 2, because in lecture set 2, we also studied scatter plots, and we talked about how you can have varying levels of linear strength in that scatter plot, depending on basically how close the points are together and how steep the relationship in terms of their increasing or decreasing value are. That was a strange sentence. And this is the same idea here. So we're going to take the scatter plot between the two variables. We're going to assess it to see if it looks like there's a strong linear relationship. And then if there is, we're actually going to fit a model to describe that relationship, which again is the objective of this particular, of this unit. All right. So here's our scatter plot for the midterm mark versus sleep data. Just as a refresher, each of the points on this plot are just a coordinate based off of our original data set. So for example, this observation here, this is going to be the student that slept 1.5 hours and had a midterm mark of 52. So this would be 1.5, 52. Right, so each point on the plot is just a coordinate based off of one of the observations in the data set. So for example, the highest point here is going to be a student that slept 10.5 hours and had a score of 91. Yeah. And every other point on the scatter plot can be found in the same way. All right, so now what we're going to do is we're going to look at the plot and we're going to imagine that we just sort of stick a straight line on top of the point. So maybe we'd have a line that looks something like this here. Oh, sorry. Okay. So what we're trying to do is visualize a straight line that kind of cuts through the middle of the points, or appears to be as close to all the points as possible. And then we're going to ask, does it appear as though the points form a linear relationship, or rather that the variables form a linear relationship with each other based off of the line that we are imagining through the middle of the points? So I've just sketched this red line here I'm looking at the points and I'm wondering, does it seem like they have a linear trend? Well, there's clearly an increasing trend. So it's certainly the case that as the students slept more, the midterm mark increased as well. So we definitely have a positive trend. There's no denying that. There doesn't appear to be any curvature or any striking nonlinearity. So it seems like the observations are fitting, relatively well to the line that we've sketched. And it wouldn't be unreasonable to say that they have a linear relationship with one another. There certainly, again, isn't any curvature or striking nonlinearity. And that's important because if we're going to use a linear model to predict one value from the other, the relationship has to be linear, right? You don't want to fit a straight line to something that's clearly curving, or has no relationship at all. So in this context, it seems like the points are fitting relatively well to the line that we've sketched out. So it doesn't seem unreasonable for us to investigate the effectiveness of regression analysis based off of an assessment of the scatter plot. Any questions so far? Okay. All right, so assuming that we've built the scatter plot, we've looked at the relationship and we can say, yeah, these appear to be linear, or it seems like a linear relationship could be useful in describing the trend between the two variables. The next thing to do is build the regression line. So the regression line has the form given in equation 1. So our regression line says y hat, which is what we recall the response variable, and the hat here means estimate of. So this is estimate of. Okay. So the whole quantity is an estimate of the response variable. So the regression line is saying we predict the response variable, which is our y variable, is equal to b0 plus b1x, where b0 is what we call the y-intercept. I'll give a more strict definition of this in a bit when we interpret it. And b1 is what we call the slope. Again, I'll give a more strict definition of this in a little bit when we interpret that value as well. And then x is called the predictor. So we're trying to use the predictor to gain a value of the response variable. And that's the point of linear regression analysis. And we're doing that through what is called a linear model, or through the regression line that's given in equation 1. So basically, what we have to do is determine what are we trying to predict and what are we using to make that predictor. So what is our response variable? What is the predictor? And that's usually defined by the problem. So for example, in our case, we've clearly placed midterm mark on the y-axis and we've placed sleep on the x-axis. So we're going to try and predict the midterm mark from the number of hours of sleep. So in our example, this is going to be the midterm mark. And this is going to be number of hours of sleep. Okay. And then the next thing that we have to do is find our values for B0 and B1. And this is done through fairly simple equations that we're going to go over momentarily. All right. So to fit the regression line, we have a formula for B0 and we have a formula for B1. B0 is equal to y bar minus B1 times x bar. So B0 is equal to the sample mean of the response minus the slope times the sample mean of the predictor, right? And we know how to compute sample means. We've been doing this throughout the semester. We just add all the values together for each and divide by n. And those formula are given below. B1, which is the slope, we clearly need this to get B0. And B1 is equal to SXY divided by SXX. And the formulas for SXY and SXX are given in the table below. But you can see that basically SXX and SYY, those are just the numerators for the sample standard deviation or the sample variance. Okay, so these equations here, SXX and SYY, those calculations should be very familiar to us as well, because we had to use those to find sample standard deviation. The only difference is we're not square rooting and we're not dividing by n-1. SXY is the sum of the squares around x and y. So you can see that this formula is very similar to SXX and SYY, except that you have a sum of x times y, and then you're multiplying the sum of x times the sum of y in this equation. Right? Now, for the most part, I don't think you're going to see any questions where you need to explicitly compute these, but this is how it is done if we were starting from the raw data. Okay, so again, our initial goal is to assess if the regression line is reasonable, which we do through a scatter plot. Then we define our response and our predictor variable. And then the next step is to estimate the slope and the y-intercept, which is done using the equations on slide 7. All right. Okay, so for the midterm mark versus sleep data, we want to find the regression line for this data set. Now you can see that we're given a number of different summary statistics on slide 8. And typically this is the kind of question that you're going to see at this level. You're going to be given these types of summary statistics and then asked to work through the different types of problems that are associated with fitting the regression line. Okay, so for example, we're asked to find the regression line using these summary statistics. So we have y is midterm mark. We have x is number of hours of sleep. Right. We have B1 is equal to SXY divided by SXX. Okay. So this is going to be from above, the sum from I equals 1 to n, xy, yi, minus the sum from I equals 1 to n, xi, times the sum I equals 1 to n, yi, divided by little n. Okay, so this is just our equation for SXY, which is given on the slide above. So I'm just taking the computing formula for SXY and I'm plugging it in directly into the formula. But you could do this separately and just find SXY and then do the calculation. That would be perfectly fine. Okay, so same thing for SXX. So we're going to have the sum I equals 1 to n, xi squared minus the sum I equals 1 to n, xi squared divided by n. Okay. So this is going to give us 6,402.7 minus 82.8 times 1,077 divided by 15 over 534.6 minus 82.8 squared divided by 15. Wonder if okay, I'll just work these numbers out so that you have them. I used to have these written down somewhere. But... Okay, so 6402.7 minus 82.8 times 1077 divided by 15 is 457.66, which is divided by 77.544, which is 5.902. Okay, so this is our slope. Okay, and then B0 is going to be y bar minus B1 times x bar. So that's going to be 1077 divided by 15 minus 5.902 multiplied by 82.8 divided by 15. Okay, and that's going to be 39.221. Okay, so then our conclusion here is actually going to be the regression line. So therefore, y hat is equal to 39.221 plus 5.902 times x. Am I using i's? No, times x. And this would be the solution that we're looking for. So we wanted to find the regression line. So that is the regression line for this particular problem. All right. Any questions? Okay. All right. So now that we fitted the regression line, the next part is how do we work with the regression line? So there's going to be three things that we talk about in terms of working with the regression line. Actually, sorry, four things. One, we want to learn how to use the regression line to make predictions. So that's actually a very straightforward process. So now that we have linked midterm mark to the number of hours of sleep, we can use that line to determine a student's midterm mark given how many hours they actually slept. So for example, what grade do we expect a student who only slept 4 hours the night before the midterm to receive? Okay, so here we're going to have y hat is equal to B0, or sorry, is equal to 39.221 plus 5.902 times 4. So you can see that all we have to do here is substitute in the number of hours of sleep that we are interested in for x, because x in this problem is the number of hours of sleep the night before the test. So we're taking our regression line, we're taking the value of the predictor that we are interested in and we're plugging it into the regression line. So we have 39.221 plus 5.902 times 4, which gives us 62.83. So we're basically saying we expect a student who only slept 4 hours to score 62.83%. Okay. So again, pretty straightforward process. We have a line that links midterm mark to the number of hours of sleep. So we have our line linking the response variable to the predictor. We're plugging in for the value of the predictor and we get out that response. Okay. Okay, so second example, exact same process, different quantity. What about a student who slept 8 hours the night before? Okay, well, we just take our line. Multiplied by 8 now. Okay, and then we would have the same conclusion, except that we would just change 4 and we would change the expected outcome. Okay, so we expect a student who slept So we expect a student who slept 8 hours to score 86.44%. Right. Okay, any questions? Okay, so here is our data set with the regression line that we fitted superimposed. So this line is the line that we found using the data. So this line has a y-intercept of 39.221, and this line has a slope of 5.902. Now, to fit the regression line to the data set is a pretty straightforward process. We only need 2 points that come out of the line, and then we can fit, or we just draw a straight line connecting them. Okay, so for example, we can use 0 and the y-intercept as one of the points. So for example, here, we would have 0, comma, b0, which is 0, comma, 39.221. So this would be one of the points that sits on the regression line. Okay, and this is, again, because the y-intercept is the value of y when x is equal to 0. And you can see that just by plugging 0 into the regression line. Okay, another point that we can use would be 8 and the value that we found on the previous slide. So we found when x is 8, y hat is 86.44. So this point here would be 8, comma, 86.44. Right. And then we could use another line or another point if we wanted to, just because we have it to make the line a little more stable, but you only need 2. But we also know that this point here is going to be 4, comma, 62.83 for the same reason, because we worked this out on the previous slide. All right. So this is a visualization of the line that we fitted superimposed on the scatter plot of the data that we are working with. So this is what our fitted line actually looks like compared to the data that we are working with. And the questions that we're going to start to answer are essentially, how well is this line fitting the data? So we're going to talk a little bit about interpretation, and then we're going to get into how to assess the actual fit of the line. So how do we know that our line is doing a good job is essentially the next big question that we're going to try and answer. In context of understanding what the regression line is telling us, we can interpret the slope and the y-intercept for that line. So that will give us an understanding of what the line is explaining in the context of the problem. The most obvious things that you can take from a regression line are the direction of the trend. So we know that our lines can go up or the line can go down. So we can have a positive relationship or we can have a negative relationship. The slope will have the same sign as that relationship. So if the slope is positive, that indicates that the trend is positive. If the slope is negative, that indicates that the trend is negative as well. Okay, so the slope basically just reflects whether the line is going up or whether the line is going down. The formal definition of the slope is that it is the expected change in the response variable for a 1 unit increase in x. So the slope is telling us how much we expect the response variable to change, and that can be positive or negative, every time we increase the predictor by 1 unit. The y-intercept, b0, is the expected value of the response when the predictor is 0. So the y-intercept doesn't always have a meaningful interpretation. For example, if our y-intercept was a negative value, so say our y-intercept was like -15, this wouldn't actually have any meaning to us, because this would be saying that a student that slept 0 hours the night before the test scored -15% on the exam, which doesn't actually make any sense because you can't score in the negatives on most standard tests. Okay. So the y-intercept is the expected value of the response when the predictor is 0, but that doesn't necessarily mean the y-intercept is going to have a useful interpretation. So we have to be careful when we're interpreting this value based off of what the variables we're measuring actually are. Okay, so what does our regression line tell us? So we had B0 is equal to 39.221. Okay, so this is saying we expect that a student who slept 0 hours the night before the midterm will score 39.221% on the midterm. Okay, for the slope is telling us the expected change in the response for a 1 unit increase in x. So we would basically say here, or we could say, we expect that each single additional hour of sleep will result in a 5.902% increase on the midterm. So basically what the slope is telling us is that every time a student gets 1 extra hour of sleep, their midterm mark is expected to increase by 5.902%. So each additional hour of sleep gives you almost 6% more on the midterm. Any questions? Okay, so we have our scatter plot. We have our 2 variables. We determine the relationship appears to be linear. We fitted the regression line. How do we know if that regression line is actually a good fit? So how do we know that the line that we're using will give reasonable results? Okay, to answer this question, we can use diagnostic measures. So we're going to talk about 2 diagnostic measures, the linear correlation coefficient and the coefficient of determination. And the role of each of these measures is to give us some idea of whether or not the regression line is actually going to be a good fit for the data. Now, you may have seen examples of the correlation coefficient earlier on in the course. I believe that we had talked about it briefly on assignment number 2, but now we're going to talk about it in a little more detail. The correlation coefficient is basically a measure of linear strength between 2 variables. The correlation coefficient is its maximum, or the strongest possible linear relationships have correlation coefficients of -1 or +1. So recall that a linear relationship can be negative or positive. So if you have a perfect positive relationship, you're going to have an R of 1. And if you have a perfect negative relationship, you'll have an R of -1. Right? To compute the correlation coefficient, we take SXY, which we had learned about earlier, and then we divide by the square root of SXX times SYY. The correlation coefficient isn't technically a diagnostic measure, even though I described it as one before. We can use it to determine if a line is going to fit a data set well because it measures linear strength, but it isn't actually based off the fitted line at all. It's only based off of the data that we are working with. The coefficient of determination, which we'll talk about next, that is actually based off of the fitted model. So that's more of a true diagnostic measure in the sense that it uses the regression line that we fitted to compute. It uses the regression line that we fitted to find its value, I guess you could say. Okay, so calculating the linear correlation coefficient is pretty straightforward. Again, we're just going to take SXY and divide by the square root of SXX over SYY. So some of these values we computed on slide number 8. The other values we still need from the summary statistics given on slide 8. Okay, so we are going to use the summary statistics from slide 8. All right. So on slide 8, we determined that SXY was equal to 5 457.66. We determined that SXX was equal to 77.544. Okay, so we need SYY still. To find our SYY is equal to the sum from I equals 1 to n y squared minus the sum I equals 1 to n yi all squared divided by n. So this is going to be from slide 8, 80,615 minus 1,077 squared divided by 15. So this is going to be 80,615 minus, oh, sorry. This is going to be 3,286.4. Okay, so therefore, R is equal to SXY over the square root SXX times SYY, which is 457.66 divided by the square root 77.544 multiplied by 3,286.4. Okay, and this is going to give us, oh, sorry, stop. This is going to give us 457.66 divided by 504.8174, which is 0.907. Right. Okay, so again, the correlation coefficient can be positive or negative. So if your value of SXY is negative, that's okay. That's possible. Second, the correlation coefficient is a measure of linear strength. So in this case, we could say the correlation coefficient implies that midterm mark and the number of hours of sleep have a excellent positive linear relationship. Now, interpreting the correlation coefficient is somewhat subjective, but we can kind of sketch out some rough guidelines where the language is somewhat subjective, but so we can have guidelines for interpreting R. Okay, so in this case, plus or minus 1, this is a perfect fit. And then plus or minus 0.9 to 1, this we can think of as excellent. plus or minus 0.8 to 0.9. We can think of this as being very good. Plus or minus 0.7 to 0.8 would be good. Plus or minus 0.6 to 0.7 would be moderate. We can then think of as 0 to 0.6 as being weak, and then 0 would be no relationship. Okay. So rough guidelines. I mean, the interpretation and the terminology that you use can be somewhat subjective here, but this would be the idea. Like 1 is a perfect fit, and then you kind of range down for every 10% set until you get to about 0 to 0.6, where anything in that range is going to be from no relationship to weak. So you could further subdivide it and maybe say like 0.5 to 0.6 is weak, and then 0 to 0.5 is very weak, something like this. But the point is, as you get closer to 0, the relationship fades to the point where there isn't really any relationship at all. And as you get closer to 1, the strength of the relationship grows, where 1, either positive or negative in magnitude, indicate perfect relationships between X and Y. So they basically fit exactly on the line. Any questions? Okay. Okay, the next measure for evaluating the fit of the line is called the coefficient of determination. This is actually a diagnostic measure because it uses the fitted line in its calculation. So this is actually a quantity that would take into consideration the line you have fitted to the data when determining whether or not it is a good fit. The coefficient of determination is actually R squared. So we can find it simply by squaring the correlation coefficient. But we can also find it by using a breakdown of the sum of squares for the regression line. Okay, so you might recall from our study of ANOVA in lecture set number 11 that total variation can be split into smaller sets of variation. So with the ANOVA, we had SS total was equal to SS treatment plus SS error. With the regression line, we can use a similar trick. So we can say total variation, which is actually the same thing as SYY, is equal to, total variation in the response is equal to a sum of squares error term, which is the difference between the actual observed value of the response and the predicted value of the response, plus SSR, which we call SS regression. This is the difference between the predicted value of the response and the observed sample mean. Now, for our purposes, we don't need to worry too much about how these calculations are going to unfold. There are some formulas given below that will help you compute SST and SSR. Again, notice that SST is actually the same thing as SYY, and SSR here, this is SXY squared divided by SXX. Okay. So these are quantities that we would be able to compute based off the examples that we have looked at so far, and they use the same decompositions around X and Y that we saw when we were computing the slope and when we computed the correlation coefficient. Now, the point is, in the context of what we're trying to do, that R squared can be found by taking a ratio of SSR to SST. So we have this decomposition of the sum of squares, and then we can compute the coefficient of determination based off of that decomposition. So R squared is equal to SSR divided by SST. But it's also just the square of the correlation coefficient. So if we have the correlation coefficient, we can get R squared. If we have R squared, we can get the correlation coefficient. So we can go back and forth between the two. Now, unlike the correlation coefficient, R squared has to be between 0 and 1 because it is a squared term. So it's a strictly positive value. And basically what it measures is how close the points are to the fitted line. So it's basically a measure that gives us a sense of how far away the points are spreading from the line. But like the correlation coefficient, when the R squared is equal to 1, this implies perfect fit. And when the R squared is equal to 0, this implies no relationship. And then we can break down the strength of the relationship using the same decile pattern that we saw for the correlation coefficient. So it's two different measures that are very closely related that give us a sense of how strong that linear relationship is between the response and the predictor. So here are some different examples of R and R squared values, just to give you an idea of how the relationships would work. That one is strange. Okay, so again, the first two plots, these indicate perfect fits. So you can see here, this is when R is equal to 1 and R squared is equal to 1, or R is equal to -1, but R squared is still equal to 1. So the first two plots indicate examples of perfect fits. And this is a situation where every single point falls exactly on the line. Now you can see as you move away from that perfect fit, the value of R and R squared will start to change to reflect how far away the observations are from being perfectly linear. So for example, in the third plot, we have an excellent fit where R is equal to 9.05, and we have an excellent R squared, which is equal to 0.9. So this is basically saying to us that we have an excellent positive linear relationship, and the points and the line explains roughly 90% of the variation in the data. And we'll come back to talk about this momentarily. But the third plot is basically indicating an excellent fit. In the fourth plot, we have a very good fit. So you can see we have a negative R of 0.88, which is very strong. And then we have an R squared of 0.77, which is basically saying that the points are further from the line than they were in the third plot, but we still have a very good negative linear relationship. All right. In the fifth plot, in the fifth and the sixth plot, we have illustrations where there's no fit, or we have basically no relationship at all. Okay, so in the fifth plot, we have more or less what we would consider to be kind of like a random cloud of information. So these points are kind of scattered evenly about the line, but there's no obvious trend being shown here. And in the sixth plot, we have a parabola, and we're trying to fit a straight line to the parabola, which of course doesn't make any sense, right? So that would not be possible or advised. And then this should be a positive, right? So no relationship. That's linear. Okay, so for the midterm mark versus sleep data, we can compute R squared and R. We actually found R earlier, so we're going to use the R squared value to basically confirm this quantity. So on slide 19, we have some summary statistics based off of the fitted model. So in the first column, we have our Y values. In the second column, we have our X values. In the third column, we have the predicted values, right? So here is the response. Here is the predictor. And here is the expected value. Okay. In the fourth column, we have the sum, or we have yi minus yi hat. So this 585.32, this is going to be SSE, which is the sum of the squared error. So this is the sum of the differences between each response and each expected value. In the third column, we have the predicted, or there's expected yi hat minus y bar. So this would be SSR. And then in the third column, we have SSY, or SYY rather, or which is the same thing as SST. So based off our decomposition of the sum of square, we can show that SSE plus SSR is equal to SST. Okay. So for our data set of interest, we want to compute R squared and R. Okay, so R squared is going to be SSR divided by SST, which is 2701.08 divided by 3286.4, which is 0.8249. Okay. And then R, okay, so we learned how to compute R earlier using its direct formula. So SXY divided by the square root of SXX times SYY. But R is also just going to be plus or minus the square root of R squared. So that's plus or minus the square root of 0.8249, which is going to be plus or minus 0.8249. Okay, so now the question is, do we use a plus or minus? All right, well, in order to determine the sign of R based off of R squared, we need to understand if the relationship is positive or negative. So basically, R is always going to have the same sign as the slope. So R is going to be positive if the relationship is positive and negative if the relationship is negative. So the same way the slope will be positive if the relationship is positive and negative when the relationship is negative. Okay, so R and B1 will have same sign. Okay, therefore R is equal to positive 0.8249. Right? So R is a positive quantity because the relationship is positive. So you wouldn't have a negative R if the trend is going up, is basically the idea. Okay. So we learned how to interpret R before. This is basically telling us, oh, sorry. Okay, so R is basically telling us that we have an excellent positive linear relationship. R squared is telling us the proportion of the response variable explained by the regression line. So the general definition or the general interpretation of R squared would be as follows. 82, okay, actually, I'll just make sure we're clear. So for R squared, 82.49% of the variation in the response variable is explained by the fitted regression line. Okay. So that would be the stock interpretation of R squared. And basically what this is telling us is that it's basically telling us how far away the points are from the line. So in saying that 82.9% of the variation in the response is explained by the regression line, this is basically saying that the line explains 82.49% of the information in the response, would be a way of thinking about it. But the R squared term is easiest to understand in comparison to other values. So when you think about 82.49% of the variation being explained by the line, this is an indication of how far away the points are from the line relative to, say, a perfect fit or no fit at all. So you're much closer to it being a perfect fit than you are to there being no relationship. So that's why we have those illustrations on slide 18 to give you some sense of how R squared is changing as the points move further away from the line, right? So we have a slightly close, our points are slightly closer to the line than they are in the fourth plot where the R squared is around 0.78, but they're not as close to the line as in the third plot when the R squared is 0.9, right? Any questions? Okay. Okay, I'm gonna stop here for today. I know it's a bit early, but the next set is the last part, so it makes sense to talk about the assumptions and the inferential techniques together as one unit because those are related to one another. So I'll save that for Thursday because that isn't going to take me more than probably half an hour, 45 minutes to do. So I will stop here for today and I'll use the rest of the time oh no, SSR is xy squared over sxx. Cool. Okay, so I'll stop here for today. And on Thursday, I will finish lecture set 12 and then we can start doing review with what time we have left Thursday and then again on Tuesday before the semester finishes. So I'll hang around if anyone has any questions they want to ask about the notes or assignment 5. And otherwise, I will talk to you guys on Thursday.